Hi everyone. Today's tutorial topic is on reconstruction for atom probe tomography. And the reason why I'm doing this is because atom probe tomography reconstruction seems to be a bit of a mystery to a lot of people because it's buried in the software that you're using, even though it's one of the most important things about atom probe data analysis. And atom probe reconstruction is actually very, very simple, and I'd like to show you that, and maybe, you won't be as shy anymore and work with your own reconstructions and try to come up with something new because we need new solutions for atom probe reconstructions these days. Anyway, so the entire reconstruction protocol, and this is a little bit of a simplified version, but you can easily alter it to fit your needs, is this code here. So you can see all it really contains is this first block where I set up some of the variables and calculated the detector area, the radius evolution. Then this block here calculates the x and y coordinates, and this short block calculates the z coordinates. And so this is for wide-angle atom probes, so you can use it for a current atom probe, and it's very well summarized what we're doing these days in this article that Baptiste Gold wrote in 2011. And I've got it open here, and it's this very simple geometry. So essentially, I'll just draw it here. Essentially, what we have is, if this is the specimen axis, you've got a detector here, and you've got your atom probe specimen. Of course, this is not to scale, and your ion that might have been here goes, flies off, and hits a detector, and you get a detector impact here. And now this line is not perfectly straight, and we'll come into how to correct for this in a second. But essentially what you do is you take this impact coordinate and you back project it and try to reconstruct where it actually came from. And this is done with the following geometry here. So you've got the detector impact coordinate here, this one here, this one here. And you assume that there is a straight line between some projection point P and a point on the surface that you can use for the reconstruction. And in order to facilitate, we need a couple of values that you might be very familiar with. First of all, the detector X coordinates, the detector Y coordinates, the voltage evolution. So in this case here, I'll just plot the voltage evolution. Plot V2, so that's the voltage evolution that I've used. So you can see this is the voltage evolution of my specimen during the experiment, and that's what we're going to use. The field factor, which is a fudging factor that we've been using for a long time, which just says, okay, I've got this and this voltage right now on my tip. What amount of voltage or what amount of field actually arrives at the tip? So it's a very nice calculation, finite element simulation image in here. So you can see that we've got a certain field distribution at an applied voltage, and we want to know for a certain geometry of counter electrode and specimen how much field do we get for an applied voltage. Which of course is a bit of a fudging factor, but it's been doing a good job for a very long time. And the second value we have here is the image compression factor. And the image compression factor takes care of the fact that the near the tip, not so much far away from the tip where there is no field or should be no field, where the ions are flying in straight paths, we're actually getting the ions flying in slightly curved paths. And what the image compression factor assumes is that we have that depending on the launch angle, linearly increasing with the launch angle, we have a compression of the angle. So that the compression of the angle is proportional to the launch angle. Again, this may or may not be true, and this may or may not change during the course of your experiment, but that's what we've been using for years and years and years, and it's been working fairly well. That said, of course, one of the reasons why I use the tutorial is because I want to encourage discussion and we want to encourage development, of course. So working on these reconstruction parameters is something that's a challenge right now, and not just the reconstruction parameters, also some of the things here that I assume to be constants and may not be constants. Anyway, so what do we need for the reconstruction? The first thing we need for the reconstruction is, of course, the flight path length. So we need to know what this distance here is, which effectively is the same as this distance here or this distance here, because here this is all nanometers, whereas here this is centimeters, millimeters, centimeters, meters, whatever, long distances. This is a reconstruction for lava tub. I found in the envelope file that it's 103 millimeters flight path. And which brings me actually to a next very important thing, which is stay consistent with your units. Always check your units, because your flight path length might be in millimeters, your detector coordinates might be in centimeters, and especially in the data that I got, there was a combination of all sorts of units in there, and I sort of had to figure out which one's which. Anyway, I'll figure it out. Just make sure that there is unit consistency in your reconstruction. The next thing is detector efficiency. In the envelope file was saying 0.5. Since I'm not using this machine, I have to believe that. You should do calibration experiments with your atom probe. There's another paper by Baptiste Gold that actually shows you how to do reconstructions that you can use for calibrations of the detection efficiency. Anyway, but these two things are instrument parameters, so they don't usually change much between experiments. The next ones are specimen parameters. So I've assumed an average density of 50 atoms per cubic nanometer for my reconstruction, and an evaporation field of 33 volts per nanometer. Of course, this depends on your specimen. Look it up. And this might actually not be a constant during your experiment. This is just mainly the same species. That's why I used one atomic density. But as you can imagine, you can very easily add that here as an input parameter and make it specific to whatever ion you're reconstructing at the moment. The next thing is the evaporation field. You can do the same thing. But of course, with the evaporation field, if you want to have it per hit, you need to smooth it out. Otherwise, your radius would change like crazy, which doesn't make much sense. Here again, we've got something that boils down to the to unit consistency. The voltage in the data that I got was in kilovolts. We need volts. Alright, so the first thing to reconstruct, this should maybe better be in the XY anyway, is to reconstruct, to move ourselves into the plane that you saw in the sketch above. So if we go back to the sketch here, everything's reduced down into one plane, but of course we're in 3 dimensions. What it actually means is that if you look here, the detector, say the detector is around here. What we're calculating is for another hit. Sorry, it's not for this hit here. Let's say we've got another one that came from somewhere here, and it flew to a detector somewhere here. We want to know what this angle is. Let's call it alpha. I'll just call it angle anyway in the reconstruction. In the protocol, and we want to know what the radius here is, and that's exactly what this operation does. So it calculates the angle and it calculates the radius, so that from now on we can work with the radius and treat everything as if it was in one plane, and then later use the angle to get back into XY coordinates. Then we need to calculate what the detector efficiency is, what the detector area is, sorry, not the detector efficiency. And this is simply done by taking this radius here, so we're determining what the largest radius of all the hits is, and calculating the area here. And this works if you have cropped sort of a circle area out of your data, or if you have an atom probe where you just get this circle shaped data all the time. I'm saying that because the atom probes with microelectrodes, your microelectrode might have some contamination, and your hit area might look something like, this is your entire detector, and your hit area might look something like this. I don't know, maybe not as ugly as this, but ugly enough. And you might be cropping, this is supposed to be a circle, okay? might be cropping this area out, and so we need to calculate what the effective detector area is. There's actually a way of using all of the data, but that's a topic for a different day. Anyway, so you need to calculate the effective detector area, and that's what we're doing here. And also the radius evolution. So the radius evolution is in this case we're using the voltage. Of course there's shank-based reconstruction as well, which makes it even easier. But for now we're using the voltage. So the voltage curve, as I've showed it before, and it's just divided by the field factor and the evaporation field. And you get the radius evolution. It's very, very simple. And this actually brings you to the xy, to the actual coordinate calculation, which means we need to calculate this angle here, because then it's very easy to calculate to calculate the hit position from here, because we know where this is, and we can have an evolution of this point depending on the cumulative atomic volume that we've measured, and then always calculate the xy and the z. Very, very simple. Of course, it's first we'll calculate the uncompressed value. The compressed value. So we calculate theta prime, and theta prime is just the angle of this triangle. So this is the radius the hit radius that we've calculated before. So it's this radius here, and the other part of the triangle is this length here. And of course, this length here is very small. It's some nanometers, whereas L here is about, 100 millimeters in this case. So the simple way of calculating theta prime here is the arcus tangents of radius divided by flight path length. Very simple. And then we get to the uncompressed angle theta. Using this formula, you'll find it in the paper. And so now we've got this angle here. That said, theta and theta prime, this calculation step is only a one-liner, this line here, if you've got an atom probe with straight flight path. If you've got an atom probe with a reflectron with an electrostatic mirror in it, then you've got the problem that this is your specimen. A detector sits somewhere around here, and you have this black box bucket here, which is a couple of electrostatic meshes. What happens is your ion comes into here, flies around in a circle, and then hits the detector here. So I'll make the detector a little bit larger. And so what you would actually need is your launch angle theta here, but you can't simply reconstruct that from the hit coordinates, because you don't know what the projection properties of that is. So in this case, you're unfortunately a little bit stuffed. If you've got a straight flight path machine, it's a one-liner. Anyway, would be nice if there would be a file format where you can get the theta the theta prime. The theta prime out of the file format somehow. Anyway, for now that's not really an option. So straight flight path, you're cool. No straight flight path, not so good. Anyway, we've calculated theta, and from theta I think you can see it's pretty straightforward to just do a polar to Cartesian transform again and get the point T that we want to have. And that's exactly what's happening here. So it's the polar to Cartesian of the angle theta and the specimen radius at the time when we're evaporating this ion. And this way we'll get two things. First of all, D, which is We'll get two things. That's the distance from the axis, d, which is this distance here. So that's d. That's d. And the other thing we're getting is the Z shift. So the Z shift is simply this shift here. So that's ZP, which we're later going to use for the Z reconstruction. But of course, for the actual Z reconstruction, we don't want ZP. Later, we'll have to we'll change that, and ZP will actually change from being this to being this. All right, makes sense? Maybe not. Maybe it does. Anyway, and it's pretty trivial to then take the distance d that we calculated here. So that's this distance d, and the angle that we calculated here. So this is this alpha here. And that gives you the x and y coordinates. All right, so already 2/3 done, right? So next thing is z, and as I said before, well, the z correction, we've changed it from this value here to this distance here. So I will just go and erase this bit here, and our z prime is now this distance here. And in order to calculate the accumulated amount of dz of volume that we've evaporated, we'll just use the formula here. So we just sum up the volumes and divide it by the actual. So the dz is the atomic volume that you're removing, divided by the effective area of specimen that you're currently evaporating. And this is just simply what this formula here is. Here I've just changed the atomic density to atomic volume, because usually I work with atomic density. I'm going to change it to atomic volume. It's just the inverse. And then you have this atomic volume, and the rest is the expression of that proportionality that I was talking about. And then the z coordinate is just the cumulative sum of the dz's, of the z increments, plus the ZP offset. So it's the wide angle offset. Because as you can imagine, if you have a hit that's further in here, then this Z offset is smaller. So sorry, I'm switching back to the original how we calculated ZP. But this one is smaller than if you have a hit that's further out here. And so if you just go by cumulative volume, it will all be sort of sitting in this first plane. It's getting a bit crowded, but anyway, it will all be sitting in this first plane here. But because we have this ZP, we're taking care of the fact that it's not all sitting in this first plane here. And that is it. That is the entire reconstruction. That's how simple it is. And if you go into Matlab and take the code, then you can just you can see that if you I've run the example before. So if you just run that for it, this is a data set that I've done recently with about 20 million atoms, with the voltage curve that I just showed you before. The field factor for the reconstruction is 6, and the image compression factor is 1.8. I think it would be a completely new tutorial to just go into the details of how you get the image compression factor and the field factor. In this case here, it's a dataset of a FinFET, so I know exactly what the gate length is, and so I can do change the reconstruction until the shape of the fin is what it's supposed to be. In other datasets, there's different clues that can tell you what it should be. Say you have a grain boundary, you know the grain boundary should be flat, and there's only one combination of settings that will make it flat. So there's always something you can find to aid your reconstruction. And if you're very lucky, you have the atomic lattice. That's the ultimate, but doesn't always happen. Anyway, so you've got a detector x coordinates, detector y coordinates, voltage, field factor. It's usually for remote counter electrode machines around 6. It's my personal experience for most Matlab data I've worked with, and 3DEP data I used to work with ages ago. And in this case, the image compression factor worked out to be around 1.8. So if you run the entire reconstruction protocol, I'll just show you for about 20 million atoms. You can see it takes about 3 seconds. Let's do that faster. Maybe my computer was a bit busy. Anyway, yeah, about 2 seconds. If you do an optimized reconstruction, I have other protocols that look a little bit more complicated but run faster. You can easily do a dataset like that in a fraction of a second. Anyway, that's the simple one. And it runs in 2 seconds. And if you want to visualize that, we'll just turn it into atomic positions, just because that's how I usually work. Sorry. Pause. So I just add the master charge column to it, just because that's how I named the variable before anyway. And we'll take a sample out of it of, say, 50,000 atoms. Just because Matlab is not very good in visualizing large point cloud datasets, I prefer to use Blender for that. And there's other tutorials I have on that. And we're currently working on code to directly import atom probe data into Blender, so that might help you in the future as well. Anyway, we'll just do a scatter plot. And ta-da! There's the atom probe reconstruction, or there's my atom probe reconstruction. So go, take the code, play around with it, have fun, come up with your own ideas for reconstruction, how to improve it, and I think that will help every one of us in the atom probe community.